Let's take a look at how to take the derivative of an equation. The way I've titled this lesson is determine the derivative of an implicitly defined relation. Basically what we're going to be doing is solving for dy dx this time, getting it by itself. I'm going to talk a little bit too about how that's relevant, particularly in this example. So this is going to be example 1. Go ahead and read this together. Zoom in a little bit. We have x squared plus y squared equals 9. Okay, x squared plus y squared equals 9. If you remember from conic sections, this is going to be a circle. Let's go ahead and draw that circle. And it's not going to be the best, but be pretty close. Okay, so this question says to find dy dx. Now, what does that actually mean in terms of the circle? Well, if we wanted to find the slope of the tangent line at a particular point on the circle, let's say right here, we want to figure out what the slope of this line was. In other words, change in y divided by change in x. This is what dy over dx would give us. Now, all we would need actually is what this point is right here. Okay, so we will see at the end of solving this maybe what the slope of the tangent line might look like once you figure out what this point is. So basically, you figure out the point, you plug it into your dy dx equation, it gives you the slope of this line. So that's the application for this particular example. So how do we do it? First of all, we would just implicitly differentiate, which is what we just went over. That's going to be our first step, implicitly differentiate. Derivative of x squared is what? 2x, right? And we've done the derivative of y squared, I believe. If not, we know the derivative of y squared by itself is 2y. This is just implicit. We multiply that by dy dx, and derivative of 9 is 0. So what I like to do when I'm implicitly differentiating is just take d dx of the entire equation and go from there. So the way it kind of works, though, is you're taking d dx of each individual component. So you can break each of these down into separate derivative problems. Like I just said before, the derivative of x squared with respect to x is just 2x, no implicit needed. d dx of y squared is 2y times dy dx. Again, we do implicit because we're taking the derivative of a function in terms of y with respect to x. And the derivative of constant is always 0, no matter what. Okay. So, next step we're going to do is isolate all of the dy dx terms on one side. So notice how this is, need to circle the whole term. This whole term has a dy dx in it. We need to get it by itself. So basically, we're going to be moving the 2x over by subtracting it. So once we subtract it and we move it to the other side, we get 2y dy dx equals negative 2x. The question is now, how can we solve it from there? Well, next step is going to look a little weird at first, but it's because sometimes you have multiple dy dx's, which we'll see in further examples. The next step is to pull out dy dx. So if there were more than one dy dx, you'd pull them both out. In this case, we're just going to move this dy dx to the left, basically, and pull it out. This step is important, again, because a lot of times you have multiple dy dx's. You don't have to do it for this example, since there's only one, but I'm just teaching you this step so you'll know it for the future. When you pull it out, it'll be dy dx times 2y equals negative 2x. Now, this leads us to the fourth step, which is going to be get dy dx by itself. In order to do that, for this example, we will just divide both sides by 2y. That will get this dy dx by itself. It will, in effect, cancel this 2y on the right, and you'll just be left with, it'll cancel the 2y on the left. You'll be left with this on the right. So it will look like this. Dy dx equals negative 2x over 2y. And we have accomplished step 4, which is to get dy dx by itself. Step 5 is to simplify, and we know that negative 2 over 2 becomes negative 1. We can pull the negative out front, so the final answer is dy dx equals negative x over y. Going back to our circle analogy, now this one's not nearly as good as my first one, but that's okay. They want to know the slope of this particular line, and we say this tangent line, let's say it crosses at one single point. Again, I didn't draw that perfectly, but you get the point. We want to know what the slope of that line is. And let's say we know that the point is negative 4, 3. Well, all we have to do, we plug in -4 for x and 3 for y, right? Because those are the points. It'd be -4 over 3, and we get 4/3. Okay, that would mean the slope of this line goes up 4 and over 3. And that's the application for dy dx, at least one of them, is finding the slope of the tangent line of an implicitly defined relation. In this case, it'd be x squared plus y squared equals 9. All right, so that pretty much does it for this example. If you have any other questions about implicit tangent lines, and we'll get to that further in another lesson, but in particular, if you have any questions about finding dy dx or getting it by itself, let me know.